All right, we're going to look at the reaction of magnesium burning in oxygen to synthesize magnesium oxide. Okay, we're going to take magnesium metal, which I've got in this little cup here, okay, and burn it using the oxygen that's already in the air to make a new substance, make a new compound, magnesium oxide. Okay, this is my magnesium here. It is fairly flexible. It's shiny, like you would expect from metal, and I can get this a little bit closer to the camera. Okay, so there's our magnesium. Okay, so I can bend it and kind of flex it like that. Okay. Now to burn it in oxygen, I mean the oxygen's already there. I just need to give it a little bit of a push, which is what this lighter is for. Now this is going to get very hot. It's also going to get very bright. So if you do this in person, you actually aren't supposed to look directly at the flame because of how bright it is and because it releases ultraviolet light. So you have to kind of be aware of that and you have to kind of be careful. Now, I want to be able to figure out how much magnesium oxide I can make from this reaction. So I'm going to catch it in this beaker. Okay, so I've already got the mass of this beaker figured out, but this is something you'd want to do in the lab before you go and burn your magnesium. If you don't have the mass of your beaker, you can burn this and it winds up down in the bottom of here, then you can't really subtract out the mass of the beaker later to figure out how much magnesium oxide was in there. You might think you could, try and pour it out, but some of it's going to get stuck to the inside, and some of it might be lost in the process of transfer. So overall, it's just better to have this weighed beforehand so you can subtract it out instead of trying to figure out how to make that work in the aftermath. Okay, so let's do the reaction. Let me get some stuff out of the way here. Okay. So I'm going to grab this with some tongs. I don't burn myself. I'll light my lighter. Okay. Can you get the end of this going? And then, come on. And I'm not going to look directly at it. I kind of look away, and I just got to make sure I don't miss the beaker. So we got a bright white flame, got a lot of smoke coming out up here. We've got a lot of heat. All right, and here, is my magnesium oxide. Okay, now you can tell by the way it broke apart that it is not the same as the magnesium we started with. Okay, so again, I'm going to kind of bring this up here. So there it is down on the bottom of there. It's now white instead of that silvery color, except for some of the little magnesium bits in there that didn't get burned. Okay, it's also very brittle and very powdery, so it doesn't flex very well anymore. You can see kind of the white color on the end of my tongs here from where I was holding it. And we had a lot of smoke come off of it too. Okay, so in this reaction, we made a totally new substance. We had a lot of energy released as a result. That's a good sign of a chemical reaction. A lot of heat and light being released shows that we have extra energy that our new substance doesn't really need anymore. Magnesium oxide is stable enough that that extra energy that kind of held together the Mg and the O2 kind of on their own is excess now. It can be released. Okay, so a lot of heat, a lot of light released. We had smoke come out, and this leftover stuff is magnesium oxide here. Has a lot of different properties. Now, we also would like to know if we did this experiment well, and if we got all the magnesium oxide we should have gotten. So in my case, I used 1.60 grams of magnesium to burn. I can use stoichiometry to predict how much magnesium oxide I should get out of that. It should take 3 fraction bars to go from grams of magnesium to moles of magnesium, from moles of magnesium to moles of magnesium oxide, and then finally from moles of magnesium oxide to grams of magnesium oxide. Okay, I want to compare that to what I actually got in this beaker, which might be quite a bit worse than what I would expect. Okay, we use the percent yield and the percent error to assess our results. So percent yield compares how much we actually got versus how much we expect to get with the math. And the percent error does a similar thing, but kind of on the other direction. Instead of saying how much did we get of what we expected, we look at how far off were we from our expected result.
Okay, let's look at some of the questions for this lab. Okay, what is the actual mass of your magnesium sample? So the piece that I got had a mass of about 0.160 grams, okay, of Mg. Okay, we use an analytical balance to make sure that we have 3 decimal places on this. Okay, so that one's pretty easy. We just, are taking down a number from the lab. We're just recording some data. Okay, now the beaker that I was going to catch my product in from the reaction, okay, is this guy right here. It had a mass of, oops, let's do black, 60.270 grams. Now, when I went and did the reaction, I caught some magnesium oxide in my beaker, and that total, the beaker and the actual yield of MgO that I made, altogether was 60.349 grams. Okay. Now, since I only want the actual yield of MgO, I don't really care about the beaker. I'm going to subtract the mass of the beaker out, so minus 60.270 grams. It's going to be equal to 0.079 grams of MgO. That was in my beaker. Okay, so we call that the actual yield because it's the actual amount of product that we made. Okay, so this is my actual yield from my reaction. Now that's going to be different from what we predict that we should have gotten based on this starting amount of magnesium, which is what we're going to look at in the next question. All right, so based on the actual mass of magnesium that we started with, we're going to calculate the theoretical yield, what we're predicting we should be able to make of MgO. So we're starting with actual mass of magnesium, which my piece was 0.160 grams of Mg. All right, I'm going to convert that because I don't want grams of Mg, I want grams of MgO. Now, if you're stuck on how we get from grams of Mg to grams of MgO, our theoretical yield, I would recommend going back and looking at your pre-lab because we've already done that there. Okay, to get from grams of magnesium to grams of magnesium oxide, we're following along with the stoichiometry diagram where we are converting from grams of magnesium to moles of magnesium, from moles of magnesium to moles of magnesium oxide, and then finally from moles of magnesium oxide to grams of magnesium oxide. Okay, the stoichiometry diagram is there to help make sure that you don't jump steps, you don't take an illegal math move, and that we have conversion factors that make sense. So for our first conversion factor, we should be getting rid of grams of magnesium, grams of Mg. Okay, on top, the next unit we're trying to get to is what we put on top of this fraction bar, which that's going to be moles of Mg. Still the same chemical, but we're going from grams to moles. Okay, now this isn't a mole to mole ratio, it's just moles on one side here, so we can be 1 with moles. So I'm going to put a 1 there. Okay, and then I recommend looking at this and asking yourself, what is this fraction bar needing from me? Well, it needs grams. What it's asking you is, how many grams of Mg are there in 1 mole of Mg? Well, that's something you can find on the periodic table because that's the molar mass. That's like the definition of it. So to find this number of grams of Mg, look at the periodic table. Okay, something that commonly happens as soon as people start seeing this G in here for grams, they just start looking through their data for something that has grams on it. Like, okay, so my beaker, so I put that 60.27 down there, and that's the mass. No, that doesn't make any sense. That has nothing to do with magnesium. Do I use the this, well, that was MgO, and that was an actual yield. We're predicting this theoretically. So that can't be it either. Okay, so whenever you're doing something in a fraction bar, you're getting a number from somewhere like the periodic table, or from like 1 mole is 6.02 times 10 to the 23rd particles. It should be something that you can look up, not that specific to our experiment or reaction. Anything like that is going to go out front like this if we want to convert it. Okay. So you can find this mass, the molar mass of Mg on the periodic table. This should help us convert and get rid of our grams of Mg, which leaves us at moles of Mg. That's our first kind of bubble to get to. Next, we'll need to get rid of moles of Mg. Moles of Mg. And our next island to jump to would be moles of MgO. This is the fabled mole-to-mole ratio. It's the only time we can't just be one with moles. But to get the numbers for this is actually probably the easiest thing, because we just go look at the balanced chemical reaction equation. Okay, so on your pre-lab, we had, let's see, balanced equation looked like this. 2 moles of Mg could react with 1 mole of O2 to make 2 moles of MgO. Okay, so this fraction bar is asking us what's the mole-to-mole ratio of magnesium to magnesium oxide. Okay, how much of this can I use to make how much of this, or vice versa. So my reaction equation is telling me if I put in 2 moles of magnesium, I should get out 2 moles of magnesium oxide. I'm literally just stealing the numbers straight from the coefficients in the equation. Okay, and if we are using a different reaction equation, if this is not Mg plus O2, it was magnesium plus like sulfur or something like that, we're getting a different chemical, then the coefficients might be different there too. Okay, it all depends on the specific chemical reaction. Okay, that's why this is an important step in the stoichiometry of figuring out how much product we're going to make. It depends on our reaction. Okay, so the last step, now that we've canceled out moles of Mg, is going to be changing our moles of MgO into grams of MgO. So I'm going to get rid of moles of MgO on the bottom. Okay, we should get grams of MgO up on top. Okay, again, this is not a mole-to-mole ratio, so I am free to be one with moles. Okay, so this fraction bar is asking me how many grams of MgO are in 1 mole of MgO. That's the molar mass. So I can go look up MgO and add up the molar mass of Mg and O on the periodic table to get this number here. Okay, now when I go and plug in my numbers, the answer I get is about 0.265 grams of MgO. Now, since you probably don't have 0.160 grams of magnesium that are burning here, you probably had, like 0.135 or 0.156 or something like that. You're going to end up with a different answer here, a different theoretical yield. Okay? But that's what we want. We want to predict based on how much you actually started with in the lab, how much MgO, how much magnesium oxide should we get? Okay, so mine came out to be like this. Your answer will probably be close, something 0.24 or 0.21 or something like that, in that ballpark. But it's going to be something around this. But it's probably not going to be the exact same unless you also happen to have 0.160 grams of magnesium. Okay, so what this is saying is I expect to get 0.265 grams of MgO out of this reaction when I do it, when I do the experiment. But what I actually got in my beaker is way less than that. I got 0.079 grams of magnesium oxide instead of the 0.265 grams of magnesium oxide I'm expecting, which is kind of rough. So this is a good sign that something went wrong in our experiment. And we can compare what we actually got to what we should have theoretically gotten in something we call the percent yield. The percent yield basically tells us how much we got versus how much we expected to get in a percentage. The percentage of what we were supposed to get when we actually got. So percent yield is going to be my actual yield, which what I got in my beaker was 0.079 grams. So 0.079 grams divided by, that's a 7, not a 2, my theoretical yield, which was 0.265 grams. Okay, I multiply this by 100 to change this into a percentage. Okay, and that comes out to be about 29.8%. 29.8% of my MGO yielded. Okay, that's not great. Okay, since this is theoretically how much MGO I should have gotten, 100% yield would mean I actually got 0.265 grams, and that's kind of the ideal. It's like, hey, we got exactly what we expected to get, what we predicted we should get. But this is way less. I only got like 30% of what I expected to get. So that can show something has gone a little wrong or something that we didn't expect happened in our experiment. Okay. In number 7, we kind of face this fact and try and figure out what could have gone wrong. Why did we end up with so much less massive product than we expected to get? My hint to you is to think about what happened in our reaction. So we had our beaker there to catch our MgO, and we had our magnesium strip there that we burned that. Okay, we released a lot of light, and some of it, the new stuff, fell down into the beaker. Well, the laws of physics say that matter has to be somewhere. It can't just vanish. So if our magnesium oxide didn't fall into the beaker, where else could it have gone? Okay, so aside from the light and heat that was released from this, you might think about what else came off of this reaction. Okay, something you could physically see. Okay. 8, 9, and 10 are all just questions about the chemical reaction that you observed, being able to tell that it was a chemical reaction and not just a physical change. The substances that we kind of started with and ended with, and kind of being able to tell, like, hey, this is a totally different chemical substance. The bonding is different. So we had to have a rearrangement of atoms to make a new substance to get there. Okay. And how we can tell physically that this is a different substance, not just by the chemical formula, but by looking, what does magnesium look like, and what does magnesium oxide look like? And what properties have kind of changed as a result. Okay, one last thing. Percent error is very similar to percent yield. It's just kind of like the other way around. Okay, instead of looking at how much stuff we got versus how much we expected, we look at how far off we were. So it's usually kind of the other piece of what's going on with our percent yield, rather than, again, seeing how much we got out of how much we expected. We're looking at how much we missed out on, or how far off our data was from our predictions and our expectations of how things should theoretically work. So we take our actual yield minus our theoretical yield, get an answer, and then divide by the theoretical yield. Make sure you do this step first. Okay, if you try and do actual minus theoretical divided by theoretical all together, sometimes your calculator will do order of operations and do this part first. And whatever your theoretical yield is divided by your theoretical yield just turns into 1, and then you're subtracting by 1, and that's not what we want. So make sure that you do your actual minus theoretical, get something, submit it, put it in, okay, or be very careful about your parentheses, and then divide by your theoretical yield. Finally, we multiply by 100 to change it into a percentage, just like we did with the percent yield. Okay, so that's basically it. Okay, and we'll be using methods like this in the future to assess our abilities in labs to see if our experimentation worked well or if there is something we didn't take into account. We might have to analyze our errors of what could have gone wrong and how we could improve the experiment to go better.